Welcome to video lecture B12. This one is on changes of basis. I'll be your advisor, Tom Roby, and here are the outline and objectives. First, we're going to construct a change of basis matrix between any two bases, B and C, script B and script C, of a finite dimensional vector space V. And then we'll analyze how the change of basis matrix from B to C is related to the change of basis matrix from C to B. It'll turn out to be a relationship that makes a lot of sense. And let's start with an example, just to keep all these things straight. There's a lot of notation in this video lecture, and I think it's sort of unavoidable just because you've got a lot to keep track of. So suppose I've got two bases for R2. That's a two-dimensional space, so each basis has to have two vectors in it. That means I can express x, any vector in R2 can be expressed in terms of either B or in terms of C. So any x is going to be, maybe alpha B1 plus beta B2, maybe gamma C1 plus delta C2, right? There's always going to be a way to write it. And so how do I go between the two in a systematic way? Well, what I first want to do is figure out if I want to convert from B coordinates to C coordinates, and the first thing I want to know is how to convert the basis vectors, B1 and B2, into C coordinates. And then if I can do that for a basis, then I should be able to do it for any vector, because I can just write any vector in terms of the basis B1. So if this is true, if I can write B1 as, say, 3C1 minus 2C2, and these numbers are just meant to be generic, but it's easier to think about concrete numbers, and say B2 is 2C1 minus C2, then what that means is that in C coordinates, B1 is 3 minus 2. And B2 is 2 minus 1 in C coordinates. Okay, so far so good. I haven't done anything tricky yet. Now here's the thing. Suppose that I know that the B coordinates of some vector are 4 minus 5, right? What does that mean? Well, that just means, when you unpack it, that x is 4 times B1 minus 5 times B2. Okay? Nothing exciting yet, but now let's look at these next few steps. If I want to figure out what x is in C coordinates, then, well, that's figuring out what 4b1 minus 5b2 is in C coordinates. But the coordinate map is linear. Remember that it's a linear transformation, in fact, a linear isomorphism. So that means that this is the same thing as 4 times b1 in C coordinates minus 5 times b2 in C coordinates. Okay, but I didn't know what b1 and b2 are in C coordinates. So I just get 4 times what b1 is in C coordinates minus 5 times what b2 is in C coordinates. And that's by our original definition, in fact, of vector matrix multiplication, just equal to this matrix times 4 minus 5, right? The 4 minus 5 linear combination of these columns is just that matrix. And so what's that matrix? Well, that matrix is what I get when I take B1 and write it in C coordinates, make that the first column. Take B2, write it in C columns, make it the second column, right? And there it is, okay? And so if you work out what this is, you get 2 minus 3. So in other words, whatever 4 minus 5 was in terms of B coordinates, 2 minus 3 is in terms of C coordinates. Now, a couple of things to notice here. One is that I didn't actually tell you what B1, B2, C1, and C2 were. I don't actually need to know exactly what they are. Just if I have any two bases which are related in this way, if B1 is 3C1 minus 2C2 and B2 is 2C1 minus C2, then I can always translate from one basis to the other by taking my vector in B coordinates, multiplying it by this change of basis matrix, and I'll get the output in C coordinates. So what I've said here in this fancy notation is that if I look at the vector x in C coordinates, or maybe I start with it in B coordinates, I multiply it by this change of basis matrix, P goes from B to C, I get the thing in C coordinates. Right, but what is that change of basis matrix? Well, I just figured it out, right? It's exactly take B1, write it in C coordinates, take B2 and write it in C coordinates, and make those the columns of the matrix. Okay, so I hope this makes some sense, right? That if I want to change the matrix that changes B coordinates to C coordinates should be formed by first writing those basis vectors in terms of C coordinates. And then making the matrix. So let's just do a reality check. This is a really good thing to do to make sure you haven't got it. It's easy to get this backwards somehow. and I do it myself and I have to straighten things out. So you want to have reality checks floating around. So what is 1, 0, b? Right, so what would that mean? I put 1, 0 in here. Well, 1, 0 just picks out the first column, right? It means 1 times the first column plus 0. So I just get 3 minus 2. And of course, 3 minus 2 is exactly B1 and C coordinates. Okay? So that's good, right? Because I should get, when I take 1, 0, 1, 0 just means 1 copy of B1. And 1 copy of B1 is the same thing as 3 copies of C1 minus 2 copies of C2. Okay? And so where B goes to C takes it is exactly to the expression of B1 in terms of the C basis. Okay, so I hope that made some sense. And let's just think for a second. Suppose C were actually the standard basis E1, E2, right? Just 1, 0, 0, 1, right? Then what would I be getting? Well, then I'd be writing, then saying B1 is 3 C1 minus 2 C2 would just be saying that B1 was 3 minus 2 in the usual way. And 3 times 3 this way and minus 2 that way, right, in terms of the xy plane. So in that case, 4 minus 5 in these weird coordinates would be being converted into what it is in terms of the standard basis. And that would just be the coordinate map. But here, instead of thinking of things as going through the coordinate map, we just want to go directly from one basis to another. And this turns out to be very useful in applications. Sometimes you're given something where the natural basis is not your standard basis, but some other basis. And the basis that you really want to look at it in, that helps you understand how the transformation operates, is actually yet a third basis. So this comes up all the time, and it really makes things easier to understand in the long run. So here's the general theorem that I just illustrated for you. Suppose that B is B1 through Bn, and C is C1 through Cn, and these are two bases for V. Then the unique matrix, it's easy to see it's unique, P taking B to C, there's no standard way to read that. PB goes to C, PB from B to C, I mean, you can call it whatever you want, is take the basis vectors BI, write them in C coordinates, and just make those the columns of the matrix. We know that that's unique because the whole point of a basis is that it has a unique way of expressing any vector in it. Right? That's what you get for being spanning and linearly independent. So this is the change of basis matrix, and it has the property that when I take x expressed in B coordinates and I multiply it by this matrix, I get x expressed in C coordinates. Okay? So there's no new ideas in here, and the same algebra just applies, except that you're working in n dimensions instead of 2 dimensions. So let's look at one more example. Suppose that I look at bases of P2. So this doesn't have to be r to the n at all. I mean, it's interesting still in r to the n, but we could be working with any finite dimensional vector spaces we like. And so let's look at the polynomial ones. Here's one basis set of basis vectors. 1 minus t, 1 plus 4t plus t squared, and 4 minus 2t squared. Just trust me, that's a basis. Okay? It's not hard to see directly that they're linearly independent and that they span. In fact, you only need one or the other. It's not hard to see that they're linearly independent, and then that implies that they span because you've got the right number of them, because we know that this is a 2-dimensional vector space. C1, similarly, you've got 3 vectors, and these ones are obviously linearly independent, because if we had, alpha times this plus beta times this plus gamma times this equals 0, well, then the coefficient of t squared would just be gamma. That would have to be 0. And then if gamma is 0, then the coefficient of t would just be beta, and so that would be 0, and so on. So that, again, we've got this triangularity thing going on. And that's actually going to make it easy for us to see. For example, if I want B1, I want to write B1 in terms of C1 and C2, how do I do it? Well, if I need a minus t, then I've got to use, there are no t squareds, I have to use negative 2c. Yeah, I have to use the negative of c2 to get the minus t squared, and then I'll have minus 1 minus t, so I'll have to add 2 to it in order to get plus 1 minus t. Okay? And similar computations show you that B2, 1 plus 4t plus t squared, well, I have to use a 3t to get the t squared, and then I also get along with that, I'll have a t and and a 1. Now if I need 4t, I need 3 more t's from here. So I'll add to this. I'll have 1, then I'll have 3 plus 3t, so that gets me my 4t, but then I'll have a 4 here, and so then I'm going to need to subtract 3 times 1 in order to get 1 plus 4t plus t squared. And in exactly the same way, analogous way, you can see that B3 is equal to that linear combination of C1, C2, and C3. Okay? So now think for a minute, what is the change of basis matrix going to look like? Maybe pause here and see if you can write it down. Right? So the key thing is that each of these expressions tells me how to write each of the BI's in terms of the C's. And so here's the change of basis matrix. B1, written in terms of the C's, is 2C1 minus 1C2 plus 0C3. That's 2 minus 1, 0. This guy is minus 3, 3, 1. So I write that down in this column. And this one is 4, 2, minus 2. So I write that down the column. And that's all there is to it. This kind of thing will come up a lot, and it's useful to just think, right, that I'm writing that these are my vectors. Let me pick a good color for this that's distinctive. So these are my vectors, B1, B2, and B3, and I'm writing each of them in terms of C1, C2, and C3. Okay? All right, so now here's an easy corollary of the theorem. Suppose I want to know what the matrix is that goes from C to B. Well, that matrix will just be the inverse of the matrix that goes from B to C. And you can see that right up here, right? All I have to do is, if I multiply, and I guess I can write it out, right? The way this all works is that I take x in C coordinates, that's equal to P, B goes to C, of x and B coordinates. Now this is just a matrix. So if I multiply by the inverse of this matrix on both sides, then this just implies that P inverse of B goes to C times x in C coordinates is equal to x in B coordinates, right? But that's exactly what the change of basis matrix should do if it's going from C coordinates to B coordinates. So therefore this has to be equal to, basically by definition, P of C goes to B. Okay? So I hope that made some sense. And similarly here, you know, what does the product of these two matrices do? So if I start off with something in D coordinates, I convert it to C coordinates, I get something in C coordinates. Now I use the matrix that converts it from C to B coordinates. What have I done? I've just gone from D to B coordinates. So that's got to be this matrix, P, T goes to B. So both of these things should make some sense, and they're both useful ways to think about what's going on. And I think that's it for video lecture B12. Thank you for your kind attention.